Oh, man, it's hot outside. Need some chapstick. Oh, it's melted. I wish I had something to keep it cool so it doesn't melt.
Hi, my name is Levi.
And my name is Allen.
We'll be presenting the Frosty Flask. Before we go over the process of building the Frosty Flask, we're going to discuss the problem statement, the design requirements, and the previous solutions.
Our original idea, called the gripper stickers, was a plan to replace the grip on the bottom of basketball shoes. However, this idea did not work because it failed the test procedures. So, we found a new problem. On average, Americans spend $200 million on chapstick every year. The majority of these people would agree that having to deal with melted chapstick is very frustrating and can be a waste of money. Unless chapstick is stored in a cool area, it will melt and the chapstick will become very difficult to use, and you may have to purchase another stick that will quite possibly melt in the heat the next day.
In order to accurately assess our problem statement, we created a survey for chapstick users with 3 questions on it. Number 1 was, have you ever experienced melted chapstick? Number 2 was, if so, would you be interested in a solution to this problem? And number 3 was, if there was a solution to this problem, how likely would you be to buy it? Here are the results for 52 responses of the random sample. As you can see, a majority of the people would agree that chapstick melting is a problem and they would be interested in a solution.
Here are some previous solutions for chapstick found online. Most of these solutions do hold the chapstick, but they do not offer any sort of cooling technology for the chapstick.
After reviewing the list of previous solutions, we came to find through the design matrix that the aluminum keychain holder was the best design for the chapstick, so we will be using that idea moving forward.
Here's one patent we found on the internet. However, it does not have the same cooling features that we are trying to incorporate into our final design.
We researched designs for specific patents that had cooling technology for chapstick. However, we did not find any. Here are some of the design requirements we found necessary. Must keep chapstick cool for multiple hours in high temperatures. Must be durable. Must be easy to take chapstick in and out. Must be waterproof. Must be easy to carry. Must be cost effective. Must be easy to store. It must be easy to...
In order to bring our ideas to life, we drew potential designs that will be reviewed and placed into a matrix to determine the best design. Here are the 6 designs we came up with.
As you can see, some of our designs don't fit all the requirements. However, design number 5 fits majority of the requirements and is the easiest to make.
In order to assess if the design we chose actually has merit, we used the 5 principles of STEAM in order to see how we can incorporate those 5 principles into our design. We will use science, technology, engineering, mathematics, and art in our project. Here are examples of the ones below. Science. We will use science to get accurate measurements and test our product in the heat. We will record this data and put it into a lab form. Technology. We will use technology to weld and to compact our product while we are making it. We will use specific machines to help us build this project. Engineering. We will use engineering to calculate exact measurements and specific parameters we need for our chapstick. Mathematics. We will use mathematics to determine the exact measurements needed to build the product and fit well in the keychain and hold the chapstick well. Art. We will use art to give the product a classic look and make the product attractive to others. The incorporation of these 5 principles show that the design has merit and is able to be constructed. Now we will move into the process of building the prototype. The process overall was fairly simple. We started by cutting 2 very long steel pipes into a 2-inch long pipe and then a 3-inch long pipe. We eventually sanded those down so that they would be approximately the length of the chapstick. We then welded the bottom of the pipes, and after we welded them, we began putting insulation inside of the flask. Next, we cut a very small piece of steel into a ring in order to make a cap for the top of the flask. We then welded the top of the flask in order to seal all the insulation in so that heat cannot get inside the flask.
Now we will be moving into the test procedures.
Before we begin testing, we had to document our test procedures. Here are our test procedures. Firstly, our test will consist of 2 tubes of chapsticks. One of the chapsticks will be a control and the other will receive our treatment. The treatment consists of placing the chapstick in the Frosty Flask and closing it. We will then place both chapsticks in the car with an outside temperature of 80+ degrees. Both chapsticks will be placed inside of the vehicle for the same amount of time, 2 hours. After, we will take both chapsticks out of the car, one without the Frosty Flask and one with the Frosty Flask. We will then compare the temperature of the chapsticks in degrees Fahrenheit.
Okay, so for our test, we're gonna place the chapstick without the Frosty Flask and the chapstick with the Frosty Flask in the same place in the car. The car will heat up on the inside. It'll be about 81 degrees outside, and we'll leave it in there for 2 hours, and we'll take them out and see which one has a higher temperature and if they're melted or not.
After the 2 hours of both chapsticks being in the car, one in the Frosty Flask and one not in the Frosty Flask, we removed both of the chapsticks from the car and came to find that the first chapstick, the one that was in the Frosty Flask, did stay at a cool temperature of around 80 degrees, while the one chapstick that was not in the Frosty Flask was around 95 degrees.